All right, gang, welcome back to another day of remote learning as Mr. Charest tries to maintain his tenuous grip on sanity. So today we're going to talk about polar coordinates. We've dealt with coordinates before. You've been dealing with coordinates for a long time. The coordinate system that is primarily used is the Cartesian system that is working with a plane using two perpendicular axes, traditionally called the x and y axes, and a point in this system. It's the x coordinate comma the y coordinate, the horizontal placement comma the vertical placement, where x is our traditional input value and y is our traditional output value. So that's the Cartesian system. We've worked with that for years. The polar system's a little different. It is still working with the same exact plane as the Cartesian system. We're just referring to different axes and different orientations. In the polar system, there is a polar axis. The polar axis is this horizontal ray. It's also acceptable to extend it in the opposite direction, and we'll talk about why that is when we get further in depth with the polar coordinate system. But this is our polar axis. And this point here is the pole. So where the axes meet in the Cartesian system, that's the origin. Where we start, our center of everything is the pole for the polar axis. So we have the pole, we have the polar axis. It is the horizontal ray going to the right of the pole. Instead of working with horizontal and vertical locations, though, the polar axis is dealing with rotations. So if we were talking about this point here, that point is r units away from the pole. So our first polar coordinate is r. That's the distance away from the pole. And traditionally, it's just r for radius. That's why they use the variable r, because there's an infinite number of points that are r units away, and that distance is the radius of the circle containing those points. And then there's the standard position angle. The standard position angle starts at the positive horizontal axis and then goes around counterclockwise. And that standard position angle is theta. That's our second coordinate. So our points, it's two coordinates, except instead of a horizontal and a vertical distance, it's one distance, the distance from the pole, and the angle that would reach that position. So from the angle from our polar axis to that terminal ray. Unlike x and y, traditionally, r is our output and theta is our input. That's not every time, but most of the time that's how it is. Now, most of our polar functions, most of our polar relations aren't going to be functions. I apologize for saying functions. It's because if you're doing rotations, there's probably going to be more instances where a vertical line is going to pass through it more than once. So we're not going to have functions in the way that we've had before in the Cartesian plane, but we're going to have a lot of specific relationships from the polar graph. So, our polar plane, usually it will look like this. It's going to have a vertical and a horizontal axis that's sketched in, and then a bunch of concentric circles. That's usually how our polar plane is going to be drawn. And the circles continue out, but they all have the center at the pole. Now, if you had a point on this polar plane, so let's say I had on this third circle, so we'll say that point is 3, and just for the sake of giving us a nice angle, let's say that that's at 3 pi over 4. Most of the time, you're going to be working with radians. Very, 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 very rarely are polar functions going to be using degrees. We, in this class, are going to be working exclusively with radians. I'm not going to do anything with degrees, so don't worry about working within degrees. We're just going to work with radians. It's going to make it a lot easier, largely because a lot of what we're going to be doing is with technology. And if you're working with degrees, to do one full circle, you're going from 0 to 360. That's a lot of processing for a computer or calculator to do, as opposed to going from 0 to 2 pi, which is just 0 to approximately 6.28. So that's part of the reason. It's going to simplify the numerical calculations that are going to be done by the technology. And also, we're dealing with locations in the plane. We're dealing with almost more distance than we are with the angles. So this point, we're going to work with the distance relationship, the angle measure that more directly relates to distances, and that's radians. So this point, it's 3 units away from the pole, and it's 3 pi over 4 is the standard position angle. But that's not the only standard position angle that represents this. In fact, there's an infinite number of standard position angles that represent this. Because you could continue going and get any coterminal angle that ends at that position. And you can go backwards as well. So this point could also be 3 negative 5 pi over 4. Or really, 3 pi over 4 plus 2n, where n is an integer. So that every polar coordinate, there's an infinite number of ways to represent it. So that's how we can represent that polar coordinate, and any of those work. But there's also more ways to represent that. And it's because r is a distance. So if it's a distance, positive means going in that direction. But a negative r means we're going in the opposite direction. So if we had negative 3, 3 pi over 4, that's at the angle 3 pi over 4, but going 3 in the opposite direction. If you have a negative radius, you're going to that terminal ray, but going in the opposite direction. So this point could have been negative 3, negative pi over 4. Because it's at the negative pi over 4, which is here, going 3 in the opposite direction. So that's another way to represent that point. So every single point has an infinite number of iterations. There's the manipulations you can make on the angle to get the coterminal, and then the manipulations you can get on the r going in the opposite direction. And then you can manipulate that angle if you want to as well. So there's not always just going to be one point in the polar plane. There's usually going to be several. And if you have 2 points, you can find out where they intersect. So this is our polar axis. That's our pole. Let's say we have the points 2 pi over 3. So 2 pi over 3 is here, and I'll say that's 3. So 2 pi over 3. And then we'll do 5 pi over 6. So pi over 6 is along here. Let's say that's about 5 away from the pole. Anytime there's 2 points, even though we're dealing with a different coordinate system, it doesn't change the fact that through any 2 points is exactly one line, and 2 points can be connected by a line segment. So if we wanted to know this distance, we're not going to be able to use our traditional distance formula, the square root of the difference in the x's squared plus the difference of the y squared. That's not going to work because there's no x's and y's. We would have to convert this to x and y, which isn't really practical. It's not really the best way to do this. The best way to do this is to draw this radius. And this radius, that's 5, that's 3. Oh, look at that, we have a triangle. And we know 2 sides of the triangle because that's 5 units away from the pole, that's 3 units away from the pole. So we could easily find out that angle. Oh yeah, that's 2 pi over 3. That's that's pi over 6. 2 pi over 3 minus pi over 6. It's 4 pi over 6 minus pi over 6. That's 3 pi over 6. That's a right angle. That's pi over 2. All right. If that wasn't a right angle, we'd still be able to just use the law of cosines to find out d. But since it is a right angle, I'm just going to use the Pythagorean theorem. 3 squared plus 5 squared equals d squared. So that's 9 and 25, so it's root 34. And again, it's just a triangle. You could just use the law of cosines if it wasn't just a right angle. Just the angles I chose ended up giving us a right angle. Now, if we want to go back and forth between Cartesian and polar, it's really all just based on trigonometry. It's really just trigonometry to help us do that. If you have a point, x comma y, I'm going to put it in the second quadrant for kicks and giggles. There's still the pole, and you know that this distance is x, that distance is y. Well, in this case, it'd be the absolute value of x. Then the absolute value of y would be positive anyway. So you could find out that. That would be r. R is just the square root of the sum of the x and y coordinates squared. So I hope that makes sense. And if we wanted theta, theta would be this. And with x and y, you could find out that angle right there. And with that angle, you have the reference angle. And just judging on the quadrant, you would use the quadrant to get the angle, to get theta. You find your reference angle and then figure out what theta is. So it's just trigonometry and the Pythagorean theorem to help you get from rectangular form or Cartesian form into polar form. Going the other way though, it's still just going to be trigonometry, just different functions, different relations. So we have our polar axis here. If we had our point, and just for fun, I'm going to put it in quadrant 4. R comma theta, that's r, that's theta. Well, we're looking for x and y, so we can make that triangle again. With theta, you can find out this reference angle. And then with r, y is opposite from that reference angle. So it's going to be r sine of alpha. And then you figure out whether it's positive or negative. Oh, so the sine, sorry, make that easy. We can just do sine theta, because if theta is in quadrants 3 or 4, the y is going to be negative, or the sine is going to be negative, so the y would be negative. And for x, you could do r cosine theta, because if the if the point is in 2 or 3, the cosine would be negative, so the x-coordinate would be negative. So it's just trigonometry. And going from polar to Cartesian, very easy. X is r cosine theta, y is r sine theta. And going the other way, you need to do a little bit more. R is straightforward. It's just basically the Pythagorean theorem. And you just need to do a little bit of analysis to find your theta based on the quadrant. All right? But alpha is just going to be tangent inverse of the absolute value of y over x. All right. The last bit of this basics of polar is about symmetry. So there's 3 types of symmetry in polar, as opposed to just 2 types of symmetry in Cartesian. In Cartesian, we either had even functions or odd functions. An even function, if you plug the opposite of a number into a function, it yields the same result as if you plug in the number of the function. So if you plugged in -2 and 2, it would yield the same output. For an odd function, if you plug in the opposite, you get the opposite result. So if you plugged in -2, you would get the opposite of what you plug in with 2. So we've talked about that type of symmetry. In polar coordinates, there's more symmetry. There's 3 types of symmetry. Oh, and I'm just going to go back to this. This reflected over the y-axis. And this rotated about the origin 180 degrees. So the even function reflected over the y-axis. In a polar graph, there is no y-axis. But there is something happening at the y-axis. There is still a line there. It's still a plane. Lines still exist in the plane. So there is still a line there. It's just not called the y-axis. But this line, it's perpendicular to the polar axis. So this angle is pi over 2. So this line, it's every distance from the pole at the angle pi over 2. So regardless what r is, if the angle is pi over 2, it's going to lie on this line. If r is positive, it gives you this top half. If r is negative, it gives you this bottom half. So we can reflect over this line. Reflections don't stop happening because we're defining our coordinates differently. So if we had r theta, if we reflected over the y-axis, it would go to about here, this point. That distance would still be r, and this angle would be theta. So, if we want this point, the radius is still r, but the angle, it's no longer theta, it's theta less than pi. Or it could be negative r, along this angle, which would be theta in the negative direction. So, if you reflect over pi over 2, r theta becomes r pi minus theta, or negative r negative theta. Either of those work because they would end up at the same position. So I hope that makes sense. So we can reflect over what was our y-axis in the polar plane. We can also reflect over the x-axis. We didn't have this type, well, there was that type of symmetry in the Cartesian plane. It just wasn't with functions because it would fail the vertical line test. But if we have our polar axis, and we can extend the polar axis in the opposite direction because at the angle 0, these are just the negative radii at the angle 0. So it's acceptable to say the whole thing's a polar axis. Some mathematicians say the only part of the polar axis is this right side, just the positive side. There's merit to both arguments. I don't care which one it is. I don't have a stake in this fight. So this time, if we want to reflect over this axis, over the polar axis, which could also be called theta equals 0, if we have a point, say it's r theta here, where this is r and that's theta. If you want to reflect it over this horizontal axis, over our polar axis, that point's going to end up down here. That distance doesn't change, so it can still be r. And this angle is theta, but in the opposite direction. So you could say r negative theta. Or if you want to go along this angle, it would be this part that's theta, so it's pi minus theta is your angle, with a negative r. All right. I hope that makes sense. And yeah. So that's reflecting over the vertical, reflecting over the horizontal. There's one more type of symmetry, and then we'll be all set. And it is reflecting about the pole. Rotating 180 degrees about the pole. So we have our pole, we have our polar axis, and if you want to take a point and rotate it 180 degrees about that polar axis, this is the easiest of our transformations. This is the easiest of our transformations to give us symmetry because we're already working with an angular rotation system. We're just trying to go to the opposite side. Well, that's just pi. So it would be the same r, and it'd just be theta plus pi. That's it. That's all you have to do to rotate 180 degrees. Just go pi radians beyond it. Or pi radians before. You could subtract pi because that's the same pi over here. But it doesn't really matter. All right. Hope that makes sense. Oh, another way to do this one, another very easy way to do it, is if you're already going at theta, you would just want to go r in the other way, so you could just do negative r. All right, so that's the basics of the polar coordinate system. Have fun.